This chapter discusses light as traces of ray traveling through different media. When light is incident upon a surface or interface between two different media, it will either be reflected or refracted through the surface or interface. We shall start with the former first in this particular video. This chapter is of special interest to people working in photography, optics, and animation industry, especially those doing digital rendering. For how do we visually perceive the world around us, if not from light? And in this regard, I'm referring to visible light, though the idea can easily be extended to other spectra of EM wave, that is either originated from or reflected by the objects around us. For instance, we know that a leaf is green because the leaf mostly reflects the green spectrum of the visible light. We then perceive different shades of the tree from the intensity of light that is reflected, and from there, we are able to deduce the 3D shape of the tree. Despite of its location behind the building, a tree can be seen because the reflected light rays from the tree are passed through the transparent window. And in generating the image of the villa on the surface of the swimming pool, light rays are reflected twice. First, they were reflected by the villa to the pool, and from the pool to the observer's eyes. A pure white object reflects all EM wave, whereas a pure black object absorbs all EM wave spectrum that is incident upon it. Nonetheless, at the very essence of it, light reflection follows what we refer to as the law of reflection. When a light ray is incident upon a flat surface at certain incident angle, normally taken with respect to the normal of the surface, let's denote this angle theta I, it shall be reflected at an angle which we shall denote theta r, equal to the incident angle. That's the law of reflection. When the surface is smooth, such as a mirror, we should then expect incident light rays to be reflected in uniform manner, resulting in what we technically call specular reflection. On the other hand, if the surface is rough, we should then expect incident light rays to be reflected in random direction, resulting in what we technically refer to as diffuse reflection. Notice that, although the light rays are reflected in random direction, the law of reflection in individual light ray is still obeyed. It is the uneven section of the surface that reflects individual light ray in different direction. Yet, each individual reflection obeys the law of reflection. Some light rays may even be trapped in the surface and reflected a few times before it is reflected away. In nature, both types of reflection coexist. Subsequently, we shall restrict our discussion to specular reflection. In such situation, we are able to see images of the real object. Furthermore, in this particular video, we shall look at images formed by a plane or flat mirror. An image is a replica of a real object, where it appears as if light were actually coming from it. Any observer from any position who is sighting along a line at the image location will be able to view the real object as a result of the reflected light to the observer's eyes. Now each observer sees the image in the same location regardless of the observer location. Thus, the task of determining the image location of a real object is akin to determining the location where reflected light, or its extension, intersects. I will explain soon what I meant by extension of reflected light. Hence, to find out how an image is formed, we shall draw the so-called ray tracing diagram. Let's say a real object is placed at S distance away in front of a plane mirror, as seen from the top. I use A and B to indicate the orientation of the object. A light ray comes from point A. By the way, when I said a light comes from point A, I wasn't necessarily implying that A had to produce its own light. For all we care, A might have reflected the light that originated from, say, a light bulb somewhere else. Anyway, a light ray must come from point A and reflected by the mirror in accordance to the law of reflection. Another light ray comes from A and reflected by the mirror somewhere else. If we are to extend these light rays that come from A to the world behind the mirror, we can then find the position of the image of point A, that is A prime. We can do the same thing for B. In fact, we can apply the same procedure to any point on the line AB, resulting in the image line A prime B prime. Take note that you need at least two independent light rays to find out the position of the image points, because this light is a two-dimensional world. In a three-dimensional world, you need at least three independent light rays to triangulate the position of the image point. If the world in front of the mirror is real, we call the world behind the mirror virtual or imaginary world. Thus, any image that is formed behind the mirror will be called virtual image, as opposed to the so-called real image which we'll learn in the next lecture. Lastly, from geometry we can easily conclude that the image of a plane mirror is located in the exact same distance away from the surface of the mirror as the real object is. However, by convention, any distance in the virtual world is negative. Hence, if we denote this distance by S prime, then the relation between S and S prime is given by this very simple equation.